Hello, in this new opportunity, we are going to solve a problem related with the Lagrange equations. Okay, the problem says a bed of mass m slides without friction along a wire which has the shape of a parabola y equal to ax squared as is shown in the illustration, with axis vertical in the Earth gravitational field G. The first requirement is find the Lagrangian taking as generalized coordinate the horizontal displacement x. B. Write down the Lagrange equations of motion. Okay, guys, in this opportunity we are going to solve this problem, and the first step is to write the kinetic energy T as 1/2 of the mass multiplying the velocity square, right? The velocity with, or the velocity that the mass has. All right. If we come back to the illustration, whatever the velocity is or whatever the direction is, for example, the mass may be moving downwards or the mass may be moving outwards, it doesn't matter. For example, if the mass is moving in the direction that I am drawing, this is the velocity. That velocity is a vector. I mean, a vector is a physical quantity who has magnitude and direction. So the vector, the velocity is a vector, as we know. This quantity is going to have two components related with each coordinate, each Cartesian coordinate. For example, the x component and the y component. That means that I can write the velocity as the addition of its components, in this case bx plus by, and the kinetical or the kinetic energy. The kinetic energy is going to have this form, 1/2 of the mass multiplying, in this case v squared is equal to vx squared plus vy squared. The velocity is gonna be, we are gonna write the velocity down as vx squared plus vy squared. We are gonna use a notation here. If we remember, the velocity is the derivative of the position with respect to time. Okay, the velocity is the derivative of the position with respect to time, but we are going to use the Newton's convention for the derivative with respect to time, and that convention is r dot. So that means that we write the component x as x dot and the y component as y dot, and it's the same. X dot means velocity in the direction along the x-axis, and y dot means velocity of the component along the y-axis. All right, and that's the, and we can write this like this too. X dot is equal to the x dt and y dot is equal to the y dt. That's convention, is convention, but this is saying is the derivative with respect to time. Okay, that means that the kinetic energy T is equal to 1/2 of the mass multiplying the x dot square plus y dot square. That's the kinetic energy. But if we remember, we have to remember something here. This is the kinetic energy, but if we remember, according to the problem, y is equal to ax squared, as I am showing you here with the arrow. I am pointing the equation, or I'm gonna highlight it here, right here, and that's why. So what we do here is we have to replace that equation into the kinetic energy equation. Okay, how do we do that? Okay, if we know that y is equal to ax squared, we have to calculate y dot, because we know y, but we don't know y dot as a function of x. What we have to do, because we know that y dot is dy dt, we have to derive that expression. When we calculate the derivative with respect to time, we are going to replace that derivative into the equation of the kinetic energy. Alright, so we have here y dot is equal to dy dt. And this is equal to derivative with respect to time of ax squared. Okay? A is a constant, so we can take it out from the derivative and we will have the s squared dt. Okay? The next step is calculate the derivative. But in this case, we are gonna derive using the implicit differentiation. Implicit differentiation means that we have to apply the chain rule. What it is? Okay, is this a squared, a, the derivative with respect to time of x squared is 2x, that's normal derivative, and after that we have to derive x again with respect to time. That means that we have to do this, the x dt. Because we know that the x dt is x dot, this expression is going to have this form, y dot 2a x dot. Why x dot? Because the x dt is x dot. Okay. The next step is to replace or to introduce this y dot into this equation, into the equation of the kinetic energy. And when we do that, we get, we can call this equation number 2, and we can call this equation number 1. And we can write down here, we replace equation 2 into equation 1. We can do that too. When we do that, we get T equal to 1/2 of the mass multiplying x dot squared plus 2a x dot square. Remember, all this quantity is y dot, and this is equal to 1/2 of the mass. Okay, x dot square plus 2 square is 4 square. We have to, each term in the parentheses has to be a square because the whole term is in the parentheses, and we have this parentheses with this second power. So each term in the parentheses has to be multiplying by itself, like doing the square, right? The second power. Okay, 2 squared is 4 times a squared times x squared times x dot square. Okay, next step is this. This term, x dot square here and x dot square here, is a common factor. And because it is a common factor, I'm gonna take it out from the parentheses. Doing this, hence we have t equal 1/2 of the mass multiplying the 1 plus 4a squared x squared multiplying x dot square. And this is the kinetic energy as a function of the generalized coordinate. In this case, the generalized coordinate is the x position. I'm sorry. So we have here this kinetic energy. The kinetic energy. Now we are going to calculate the potential energy. The potential energy by definition is the potential energy by definition is V equal to mgy. Okay, mgy. We know y already, right? So what we have to do is only to replace the expression for y into this equation of the potential energy. That way we have V is equal to the mass multiplying the gravity multiplying y, but we know that y is a x squared, and that is the potential energy. That's the potential energy. Okay, and now we are going to calculate the Lagrangian. This is the potential. Before doing that, I'm going to write down this potential energy. And now we are going to calculate the Lagrangian, or we are going to write it down, because we calculated the kinetic and the potential energy already. So the next step is only to write the Lagrangian down. And by definition, the Lagrangian is L equal to T minus B. That's the definition of the Lagrangian. It's a function of the coordinates, of the generalized coordinates. In this case, the generalized coordinates is the position x along the horizontal axis. All right, so we have here L equal to 1/2. We know the potential, the kinetic energy, 1/2 of the mass multiplying 1 plus 4a squared x squared x dot squared minus mga x squared. This is the Lagrangian of the object with this kind of motion. Okay, this is the part A of the problem. We calculated the Lagrangian, and this is the part 8 of the problem. Okay, guys. The next step is to calculate. If we come back to the problem, it says write down the Lagrange equations of motion. Okay, we have to be aware that the Lagrangian is a function. It's different than the Lagrange equations. Okay, the Lagrangian is an equation that is a function of the generalized coordinates, but the Lagrange equations are describing the motion of the particle. Okay, so that's the difference between those two equations. Now we are going to write down the Lagrange equations of motion. To do that, in order to do that, we come back here. By definition, the Lagrange equation is derivative with respect to time of the partial derivative of the Lagrangian with respect to the generalized velocity minus the partial derivative of the Lagrangian with respect to the generalized coordinate, and that is equal to 0. Okay, so we have to do this step by step. Okay, this is the part B, and this is the Lagrangian equation, the Lagrangian equation. In order to do that, we have to calculate each term. For example, we have to calculate this term, that is the partial derivative of the Lagrangian with respect to the generalized velocity, and the partial derivative of the Lagrangian with respect the generalized coordinate, and we apply this equation to calculate the equation of motion. Okay, right. So we are gonna do the first part. The first part is calculating the x dot. Okay, that means it is the derivative. This is a partial derivative. A partial derivative means that we are going to take some variables as some terms as constant. So we are going to only derivate the expression with respect x dot, with respect the generalized velocity. Okay, we are calculating the derivative of the Lagrangian with respect to time, with respect to the generalized velocity, and the Lagrangian is 1/2 of the mass. 1/2 of the mass multiplying 1 plus 4x squared, 4a squared, s squared, x dot squared minus mgax squared. Minus mgax squared. Okay, because we are calculating the derivative with respect to the generalized coordinate, the generalized velocity x dot, so we are gonna derive with respect to this quantity. And because this whole term doesn't have any x dot with it, automatically that derivative is going to be 0 because this term is as a constant in this derivation. So this is going to be 0. Automatically we can write it down as 0, and we only calculate the derivative with respect to x dot in the first term. That means that the LDX dot is equal to, okay, all this part that I am underlying with green is going to be a constant too, because no one of those terms is x dot. So we take those terms as constants. We only derive the x dot. So we have here 1/2 of the mass 1 plus 4 a squared x squared. Okay, the derivative with respect x dot is 2 x dot, because we are derivating that term, okay? And that is, okay, these two cancels these two as well. They cancel each other. So the final term is going to be m1 plus 4 a squared s squared x dot. Why? Okay, I have a little question here real quick. Why I did cancel those two? Because one of those is on the bottom and one of those is on top, so we can cancel each other. We can cancel them, sorry, and there is no problem. Okay, thus simplification of the terms of the equation. All right, guys. The next step is calculating the derivative with respect to time. We have already this. We have already the LDS squared, the LDS dot. Now we calculate the derivative of that term with respect to time. Now we calculate derivative with respect to time of the LDX dot, and that is equal to the derivative with respect to time of the LDX dot, but we know that the LDX dot is this term, is m multiplying 1 plus 4 a squared x squared s dot. Okay, we have to apply the product rule for derivatives. So for example, I'm gonna do a little explanation real quick here, or probably you know that. I mean, if you are watching this video about Lagrangian equation, it's because you have a really strong background in math. So I think that it's not necessary to do it, but probably it's better if in a different video I explain derivatives. So what I'm gonna do is here real quick is calculating the derivative of the first term or the second term, whatever. For example, I'm gonna take the derivative for the second term first, and it is gonna be, okay, this is gonna be m. I'm taking the first, all this first term as constant, and derivating the second term s dot. So the result is 1 m multiplying 1 plus 4 a squared x squared, but the derivative with respect to time of x dot is x 2 dots, because I am derivating with respect to time this expression. Plus, now I take that term as constant. I derivate the term that I'm gonna highlight with green. I'm gonna derive now this term that I am highlighting, and I leave the other term as constant, x dot, on the second part, or on the second expression. Okay, that's gonna be m multiplying, okay, m is constant, right? So it's multiplying the expression that I'm gonna derive. The derivation or the result when I derive 1 is 0, because 0 is a constant and is adding the other term. So this is gonna be 0, and the derivation on the second part, on the second term, is gonna be, on the second term is gonna be 4, that's constant, a squared. Okay, I am derivating s squared, okay, because x is a function of the time, so it's gonna be 2x x dot x dot, and that multiplies x dot. Okay, guys, hopefully you understand this part. I think so. I think that you do it. You are really smart. So this is m 1 plus 4 a squared x squared x dot plus m 4 times 2 is a squared x times x dot times x dot is x dot squared. So that's the first part. Okay, the equation is this. So this equation is the t, derivative with respect to the time, the L, the x dot, and this is the first part of what we are looking for. This is the first part. We're gonna highlight it. I like highlighting equations, guys, because that way we don't get lost when we are looking for them. Okay, this is the first part we are looking for. Actually, I'm gonna highlight this part in the Lagrange equation too. The part highlighted with red is this. Now we are gonna calculate the second part, this part, the LDX. Okay, guys, we are gonna calculate the second part. So the second part is gonna be, we go for to a new page, and we say the L, the X is equal to derivative with respect x, partial derivative with respect x of the Lagrangian. If we remember, the Lagrangian is 1/2 of the mass 1 plus 4a squared x squared x dot squared minus mg a s squared. So the variable here, the variable with respect we are derivating here is x. That means that derivative is gonna be the LDX is equal to, okay, 1/2 of the mass. Derivative of 1 is 0, okay? This is the derivative of x squared is 2x, and 2 times 4 is 8. A squared x minus derivative of 2 squared, of x squared is 2x, and this mg that produces mg ax. Okay, So this is the second part. This is the second part. And this time we are going to write the Lagrange equation of motion, right? We remember that the first part is m1 plus 4a squared x squared x 2 dots. So we have the Lagrange equations of motion is all this part highlighted with red, m plus 1 plus 4a squared x 2 dots plus 4a squared x squared x 2 dots plus m 8a squared x dot squared a squared x dot squared. The second part, okay, this is the first part of the Lagrangian Lagrange equation of motion, and the second part is minus. Remember this sign is minus 1/2 of the mass 8a squared x minus 2m GAX. I think that I was missing this term. Oh no, it's okay. Oh yeah, I am missing this x squared, x dot squared. Sorry guys, I am missing this. I have to write it down here too. Okay, so I can we can, okay, this is equal to 0. Okay, this term we can this term has the same form of this term. They are alike. This is 1, this has this coefficient 1, and this has 1/2 as coefficient. So this one minus this is 1/2 of this. So it's gonna be m multiplying 1 plus 4a squared x squared x 2 dots 1 all this part minus 1/2 all this part is plus 1/2 of the mass multiplying 8 a squared x dot squared minus 2m GAX equal to 0. Okay guys, this is the equation of motion according to the Lagrangian. It's a really complex equation, but that is what the problem is asking for. It's a complex equation, but that's what the problem is asking for. Okay guys, hopefully this problem helps you to understand some physics. See you in the next video. Bye.